Good morning, everyone. Data enrichment is one of the most common requirements while building a data pipeline, be it batch or stream. Now, it's interesting about the stream processing pipeline while building a stream processing pipeline because latency and the throughput SLAs need to be ensured. So the question is, what kind of enrichment patterns will suit the streaming use cases? My name is Shubham Rakshid, and I'm a streaming solution architect in AWS based in UK. And today I'm going to talk about different data enrichment patterns that you could leverage with Apache Flink and the trade-offs of these approaches. Let's have a quick look what you're going to talk about. First, we'll say the context about streaming data enrichment. Then we're going to talk about some categories of data enrichment. One is the caching of reference data. Second is asynchronous and synchronous lookups. And the third is the reference data as a stream. We'll do a demo, and then we'll wrap up and open up for Q&A. So streaming data enrichment is about enriching raw events with additional information known as reference data so that the downstream system can make a complete view of the data. It helps to improve the data quality of the pipeline and also drives better decision making. Now, when it talks about enrichment is a broader subject, and it also includes cleansing, validation, filtering, and all of that. But for the purpose of this talk, I'm going to focus on how you can enrich your stream processing application with the reference data. Now, there are different streaming enrichment use cases. For example, let's say you are doing a stock market transaction kind of event, dealing with that, and you need to enrich with the maximum bid and ask for every transaction for analytical purpose. Similarly, if you are working on some OTT media service, you're trying to understand that where from the traffic pattern is coming from. Based on the geolocation information, you can enrich those events with the geolocation information. And same you can do for sensor data, and for e-commerce transactions, you could use a customer data to enrich your e-commerce transaction events. Let's first look into the first category of pattern, caching of reference data. Well, in this scenario, my reference data is static. I'm working on a scenario where I'm getting some flight events, where I have the flight number and the airport codes and the departure date time. The airport codes, I need to enrich them with the airport names. Now, there are a handful of airports in this world. It's like 1,700 or 1,800 airports. So it's not a huge volume of reference data. So how can I use the reference data to enrich these events? Well, we can preload the reference data in the tasks. And what is a task? So obviously, tasks are where the actual computation is happening. It is run by the task manager, and when you look in the task is at logical level. When you look at the physical implementation, it comes down to the subtask. And what we are doing is we are loading the entire reference data in the memory of each and every subtask. Because it's small, we can load it. That means when the Flink application starts, it loads the data from the reference data from S3 over here, let's say, and we are loading in the subtask memory, and any input data that's coming in the stream, we can enrich it from the memory and send it as an enriched stream. You can use either rich flat map or process function to do this particular operation. What are the advantages and challenges of this? Well, first of all, it's easy to implement, obviously, and it can support a low latency enrichment because your reference data is in memory. And it can support high throughput because of the high volume of data, and because of these reference data in memory, you can support a high throughput ingestion pipeline, stream enrichment pipeline. However, the challenge is the entire reference data has to be loaded in each subtask memory. So if your reference data is big in size, it's not a very scalable approach. Your task manager will run out of memory. And also, your reference data can go stale over a period of time. And if you need to refresh the reference data, you have to stop the Flink application and restart it again. So the question is, how can we actually load a large reference data? Let's take this example. We go back to the same flight event, and here we need to enrich the flight number with the flight details. Now, this flight number is very unique to the airline and the route it is operating. There's so many airline companies, and they operate on multiple routes. Each and every route has got a flight number. So this reference data is obviously larger than the airport codes that we had. So how can you do that? We cannot load the same reference data into the subtask memory. What we can do is, we can actually cache the data in the Flink state in a partitioned manner. First of all, Flink has a concept of state, and the state is distributed within the Flink cluster and is local to the task manager where the processing is happening. And it is backed by different backends. It comes out of box support for two different backends. One is HashMap state backend, another is embedded RocksDB state backend. The HashMap state backend writes to the Java heap memory, and the RocksDB state backend writes to RocksDB. With the concept of state, we also need to understand what is the keyed stream. So you get an input stream, and you can actually partition the stream based on certain key. And then you get a keyed stream. So each of these streams are being processed by a specific operator of these data. And for each and every keyed stream, you can have a keyed state. That means the state is only available to those keys, and it can be used by functions and operator that uses the keyed stream. So what's going to happen? We have the input stream. First, we need to use a key by operation and here the key by operation will be done based on the flight number, and you will get a keyed stream where you'd get two key streams, let's say EK018, another is OS454. And each of these keyed stream, when it gets processed, it will load the data from the reference database lazily for that particular key and store it in the Flink state. And once it does so the next time when the same key is repeated, it doesn't need to make a call to the reference database. It can look up to the Flink state and enrich the event. And then it sends out emit the event for the enrich stream. We can use rich flat map and process function also in this particular pattern. How does it score over the previous pattern? Well, first of all, it is also support low latency because state is local to where the processing happens. And it can support high throughput, and your reference data is a lot more scalable now because your reference data is not loaded in the subtask memory, but is actually loaded in the Flink state. And the bigger your cluster, the bigger the state. And state in Flink can go quite big. And however, the same challenges still there, that your reference data can become stale over a period of time, and how to refresh the reference data. So the question is, how can I always enrich the data with the most recent copy of the reference data? And while working on this project, you're also dealing with another stream, where you are dealing with the passenger information. You have the booking reference number and customer ID over here, and you need to enrich with the customer details, like name, passport, contact number. Not every customer are going to provide these details when they're doing the airline's booking, but probably at some point later. So if you're enriching this event, it's always important that you are handling the most recent copy of the reference data. How can you do so? Well, we could we can do it by using asynchronous or synchronous lookups. So let's have a look. First, let's have a look at synchronous lookup. For every event, we are making a synchronous blocking call to an external API, and you're getting a response from the API. Obviously, there is a wait time involved in getting a response, and while we are waiting for the response, we're not processing any more event. This will induce some latency and will also impact the throughput, overall throughput. Flink also supports the async IO function that allows you to asynchronously make requests to your external component. You can make a bunch of external requests without waiting for the response immediately. And after some time, you get a response back. You made a request with A, B, C, and D, and you got a response back from A, B, C, and D. Wait, we didn't get the response in the exact same order. And that's going to happen because it's asynchronous processing. You do not know when this request will be returned. And this is where the async I/O operation has got a feature called ordered wait versus unordered wait. If your Flink application is, and for the use case, if it works with unordered events, so you can really emit the event as soon as you get the result from the API. But if you need to order it, Flink can buffer these events and will actually hold it till all the events previous to that event is received before it emits the result. Obviously, this will impact your latency because it's buffering the event before emitting it and can have some impact on overall throughput as well. However, async I/O also has some features like timeout and capacity, like how long you would wait before you get a response back from the API. You could mention some timeout. Or capacity, like how many requests you are going to make to the external API. If you have 1 million records per second, you are not going to make 1 million records, invoke 1 million requests to the API every point of time, right? There has to be some kind of a capacity before, after which you could say that, wait, I am at capacity, I do not have ability to process more before I get a response back from the previous request. And you could do that. So how does it score over the previous two setups? First of all, here you could have access to the most recent data, and it's ideal for scenarios where you need to talk to external system. Sometimes this is a very important pattern because let's say you have a model that is hosted externally, it has got an API, and you need to invoke that model API to get those data. However, with this particular pattern, there are still some challenges, and it relies on, some of these relies on the external system itself because it can generate the heavy read load on the external system. Secondly, you cannot build a very high throughput, low latency kind of enrichment application with it because if you're making I/O calls for every event, even if it's asynchronous in nature. And your latency involves can depend on whether you're using ordered wait versus unordered wait, or even the external system you're talking to. Well, now, async I/O is good, but the I/O operations for every event is actually a concern because it reduces the throughput. So what can be done? What you could do is that we can make a synchronous lookup, blocking call, and cache the data in the Flink state and giving a TTL in the Flink state. It is exactly similar to the pattern we talked about, partition caching of data in the Flink state, with the additional TTL configuration over here. So what happened? The first event that comes in, it makes a query to the state. It doesn't get the data back, so it makes a call to the request, makes a call to the API, gets a response from the API, and write it to the state with a TTL. When you are actually using Flink state, it's always advisable to use TTL because that would ensure your state doesn't grow over a period of time. It will also make sure that the checkpointing process runs smoother and it takes a small amount of time doing the checkpointing. And when you say that we can query the state, what does it mean? How do you do that? Flink supports different state primitives like value state, list state, map state, even aggregate state and reducing state as well. For value state, it actually stores the data, the value for the specific key in the Flink state. For the list state, it holds a list of values. For the map state, it holds the key value pair, and using the key, you can retrieve the value for that particular key. Now, what is the advantage of this pattern? Well, first of all, it's simple to implement, and it also reduces the amount of I/O you are making to the enrichment API call. And it reduces the application latency as well, because you are having multiple cache hits, because you're reading from the cache most of the time. But it depends, right? If you have end up with a scenario where your keys are not repeating, and your keys are unique in nature, and then you are making multiple synchronous calls, and that impacts your overall application. So it depends on the use case where you could you're estimating that your cache hit ratio will be high and it will not have too much of cache miss. And then the TTL is also something subject to understanding that what kind of TTL will work for your use case. If you have a large TTL number or small, depending on it, because your enrichment data can go stale if there is a very high TTL, and if you are doing a too low TTL, you are making too many calls. Well, the question is then, how can you have a low latency access to the reference data? So think about, in this scenario, we are dealing with some Forex transactions, okay? And so these are some order data, and this is the currency over here. We need to figure out the exchange rate for the currency at the time the transaction happened. Now we know that the exchange rate varies actually, it's a very highly fluctuating data. So my reference data is constantly changing. How can I actually use it to enrich my stream? For that, we can actually kind of stream the reference data as a stream of events. So we have the reference data on the left-hand side in some databases. And now one way is that we could use asynchronous or synchronous lookups to the database to get the reference data out, but we do not want to poke the database so many times, it will generate a very high load on the database. Rather, we would like to actually use change data capture of the reference data because it works in transaction log. For MySQL, it works in the bin log. And then you write this into some kind of streaming source like Kafka as change events. You also have another streaming source where you are getting the raw events. Now your Flink application gets these two streams of events and then stores the rates data, change events, into the Flink state, apply the enrichment to the raw events before syncing the data to some downstream system like database. In this scenario, you can use a co-process function to do this. The advantage of this approach is that it supports a really low latency because you are always reading the reference data from the Flink state. And your state can grow, even if your reference data can grow over time, and you always have the latest reference data available to you in your Flink state. However, it's a bit complex to implement. So I have a demo about this particular pattern. So let's look at this demo. So basically, this is the physical implementation of that diagram. Here we have the MySQL database running on Amazon Aurora, which contains the rates data. We are using Debezium on Kafka Connect that can extract the change data capture events from this MySQL and write it to a Kafka topic rates. And similarly, we have another topic orders. The Flink application then stores the rate information in the Flink state and enrich the order data. I have a QR code over here. If you're interested to play with the same code that you'll be doing now later on, you can scan that one. So let's go to the console. Okay, so first, I'm going to connect to my MySQL database and create some tables, the rates table, with some information over there. So it looks like this. This looks like you have a currency, USD, Euro, INR, GBP, and the exchange rate for that one, and you have the last time stamp. One thing to understand is that when you are generating the orders data will pick up the latest rates information. That's great. However, what will happen is that the order data can be a late event as well, right? If there's a late event, how are you going to handle that? It should be enriched with the rate information that was correct at the time when the order was created. And this is what we are going to demonstrate in this demo. Then I'm going to create the Debezium connector. And also going to create some topics, order topic. Okay, so let's list the topics, whatever topics I have. And I'm expecting 2 topics over here. The orders topic for the raw events and the testdb.testdb.rates that's been created by the Debezium connector, which picks up the rates information from the database and write it to the Kafka. Now I'm going to run the Flink application. So you can see once the Flink application starts running, it picked up the rates information from the rates database and is marked as blue. I'm now going to run the order application to basically generate some order data. So this order data is getting generated, each order information, order ID, price, currency, and timestamp. And we can see that this data is getting enriched with the rate information. You can see the conversion rate is actually getting applied with all this information. Now this order generator application also generates some late events periodically. So what will happen if I generate a rate event now? First of all, you could see that one of these has got a conversion rate as 0, this one. Why so? Because this order was created basically before when the rate information was available. At that time, there's no rate information available. So that's why it's coming as 0. Now, if we actually now change the rates, in the MySQL database, what we see is that new rates data has been picked up by the Flink, and all the latest information or latest order data is using the new rates. Okay. However, the one that got generated is the late order 56. It is basically picking up the old one, which is 1.27 as the rate information, which is the one that was created before. Because this order information was created at the time the current rate was the 1.27. So that's what I wanted to show in the demo. Let me show you a quick look into the code, how it's all written. Okay. Okay. So this is my main function where it is, I generate I first write the extreme execution environment, getting the command line parameters. Then I have a class Kafka initializer. Here I am basically creating the source to read from those 2 Kafka topics and have methods which will actually create the rate and the order stream. We have like 2 data stream over here, rate and order. And what I'm doing over here is, this is the important part of it, that I'm connecting the order stream with the rate stream and applying a key by operation for the keyed stream. I want to create the keyed stream here based on the currency. In this scenario, I am doing the key by operations both in currency for order and rate, because at some point I'm doing a join. This is nothing but a join. And applying the process function, the key process function over here. The change data capture enrichment data, which I'm going to call here. So okay. In this one, you can see we are using the keyed co-process function, and here I have a stream, which is the key. This is the first stream order, this is the second stream rate, and this is the output stream order. And I'm defining a state, a map state over here. Here in my map state, it has got a key, and the value is list of rates. So for each and every currency, I'm storing all the rates that it has seen ever. And in this key process function, the two things is very important. That is process element 1 and process element 2. Basically, process element 1 says that how I'm going to handle my first stream, and my first stream is order stream. And process element 2 basically determines how you're going to handle your second stream, which is your rate stream. So whenever you are getting a rate data, I am basically looking into the state and appending that rate data to that state. And when the order data comes in, I am looking into the timestamp of the order data and comparing with the timestamp of the rate data, all the rate data, and figuring out wherever the order's timestamp is greater than the rate timestamp, it means the order was created after the rate changes happened, so you should pick up the latest rates. So that's all about the demo. Let's go back to the this presentation. I'm quite towards the end of it. So this is a this is a summary slide which basically shows how these different patterns and how this goes over the different aspect: data recency, scalability, complexity, latency, and throughput. I'm not going to read out the whole thing, but what you have learned 5 different enrichment patterns, and what are the trade-offs of this pattern, when you should actually use those patterns in your use cases. All of this pattern has got its particular use cases, and you could use either of this pattern depending on what you require over there. Well, that brings me to the end of the presentation. Thank you very much.